Lab one, lab one. Lab three, 1, 2, 3, lab three.
What's that? I do. Where you? Yeah, yeah. I'll walk with you in a sec. Yeah. Let me get Armin up and running. Yeah. I think Victory's. Yeah. They're coming. Let me get Armin up and running. I don't want to leave him.
Lab 1 volume, Lab 2 volume. 1, 2, 3. Yeah, on there it looks fine. We got the compressor on, so it is knocking that down a bit. 1, 2, 3.
Thank you, though. I appreciate it.
1, 2, 3. It's okay. Don't panic, guys. It's gonna be okay. Everything's gonna be just fine. Lab check. Other lab check.
Okay, and
you can let, before you do this, actually, wait. Give it one more minute. And then
you're doing it?
No, yeah, let me just, Wolfgang just wanted to let everyone see this. We can put it up again later. Do that. And then who's the first speaker?
Kishley.
All right. They're chatting in Slack, but there's no questions in Zoom.
Okay.
Isn't that weird? And there's 50 people.
Yeah, it's nothing.
All right, yeah, you can open it up. You can go.
Doing your sharing.
All right, all yours.
There's your clock. Okay. Remember to start it.
Yes, perfect.
Okay, everyone. Is this on?
They're on.
Okay, everyone, please sit down. Let's get it started. We all are hungry. Okay. Let's start session 6, survey science. In contrast to what's on the paper, I'm not Lou Stroger, I'm Armin Rest, I'm the chair. And our first talk will be by Kishley Day, and it's about stories of stellar birth and death. Go ahead.
Okay. Yes, thank you. Yep. Which is naturally what happens. When you unpick that, I'll give you $1. All right. Transients from audio. This is ridiculous. So is this even
You can
possible?
move to this side. There's still places here.
There you go. Okay, so you get the power on the top here for you while you put that on.
Okay. Yeah. Perfect. All right. Thank you, everyone. Thanks to the organizers for inviting me to. Oops. Yes. Sorry. Yes. So thanks to the organizers for inviting me to give this talk. I was asked to speak about sort of the history of surveys in the. Oh, this thing is falling. You guys should just hold it. I don't mind holding it. Okay, that's okay. Hopefully it will work. Hang on. Yes. So I was asked to give a history of infrared surveys, where we are and where we are going, and that's what going to be the topic of this talk. So, so I thought it would be befitting to start with sort of where we are today, and just to give you a landscape of where we are going. So I wanted to show this collage of the surveys that exist today. Of course, we all know and love these surveys. I apologize if I missed one of your favorite surveys, but this just gives you a sense of the landscape of surveys today. These are a mix of ground-based surveys that are surveying very large parts of the sky to telescopes that are even in space doing surveys that are somewhat smaller in cadence today, but that's only going to grow in the next decade. So there are many different ways in which you could visualize what these surveys are doing. But because we are at this conference about transients from space, I wanted to really highlight the advantages of going to space. And so one way to look at what these surveys are doing today is to plot these on a graph that shows at what wavelength do these surveys operate and how deep do they go. So these are all the surveys that we are seeing previously. On the y-axis, you have the rough wavelength at which these surveys operate. And on the x-axis, you have how deep these surveys go. And it's easy to visualize the advantage of space, because on this plot, you can immediately plot that this is basically what you can do from the ground, this wavelength range. Everything outside it is very difficult to do from the ground because of the atmosphere. And the excitement really is that all of, even though our existing surveys are almost confined to this space of the range that is accessible from the ground, this is going to change very soon. And if you look at what's coming online, even in the next 5 years, this is what it's going to look like in the next 5 years, which is you have this range of surveys that are going to operate in space. All the things that you see highlighted in bold, these are surveys that are running in space that allows you to go to wavelength regimes that have previously not been possible. In the infrared, of course, we have Roman, SphereX, NEO-Surveyor, and you might say that some of these are not conventionally time domain surveys, but I'll try to convince you during this talk that yes, we should be thinking of them as time domain surveys. I will not get to talk about ULTRASAT and UVEX because those are in the ultraviolet, but I'll try to hint upon some of the synergies I see between the infrared surveys and these surveys at other wavelengths. All right. So before we go into talking about why these surveys are opening up a new discovery space, let's think a bit about what science are we poised to learn from these instruments. So hopefully all of us have seen some version of this plot. This is taken from the Britannica Encyclopedia, so it's considered to be common knowledge. And this is something that we teach to undergraduates even in courses. So what we take all of this to be sort of how stars evolve depending on the mass of the star. And the bigger picture is that a star is born, it turns into a stellar remnant at some point depending on its mass, and eventually this is part of a bigger picture that where these stellar remnants that form out of stars, they eventually grow into supermassive scales and form the seeds that hold together galaxies and regulate the growth of the entire universe. Now, for this entire conference so far, and I think I'm correct, which is that all of the main session talks we've heard so far, we only heard about a very narrow part of this entire chain, which is this, the supernova, because all of our talks so far have been supernovae, supernovae, supernovae. But what I want to convince you is that there is this huge discovery space that spans across this entire stellar life cycle, and effectively every single part of this chain involves some kind of an explosive transient that we can study and observe with infrared surveys. And that's what is going to be the thesis of my talk, which is that infrared surveys are really opening up this new space for understanding stellar life cycles and what they do in their afterlives. So to motivate some of that, I wanted to show you some results that we've been getting from sort of pilot ground-based surveys and existing space-based surveys. And because most of these facilities do not exist yet. Well, SphereX was just launched last night, so kudos to the SphereX team. Yes. A lot of my talk is going to be about existing instruments, particularly things that we have been doing from the ground. These are shallow wide field instruments, all the way to things that are currently running in space, which is NEO-WISE, which just concluded last year. All right. So of course, I will not have enough time to go through this diversity of things that happen through the stellar life cycle. So I wanted to really focus on two extreme ends of this, which is the most massive things and the lowest mass things. And the first thing I want to start with is really the most massive things, which is this idea of how do black holes grow from these stellar mass objects that we can find in our own galaxy to these supermassive objects that sit in the centers of galaxies. And as you can already tell from this plot, the historical picture has been that yes, supermassive black holes grow via gas accretion, and there's no doubt that this is what dominates the growth of supermassive black holes in the universe. Although, with these JWST discoveries of massive black holes in the early universe, some of that is coming into tension. But I want to talk about other methods you could grow black holes as well. So the classical picture is that this is how a black hole grows. You have an active galactic nucleus that's accreting gas in its center and then growing to these supermassive scales. But one other channel that has been around for a long time, but we're only starting to explore at the moment, is this idea that not only is there gas in the centers of galaxies, there's also stars in the centers of galaxies. This is our own nuclear star cluster of the Milky Way. You see there's somewhere in there, you can't see it, but there's a supermassive black hole somewhere in there. And you can imagine that instead of gas being accreted into supermassive black holes, growing it in size, you can also have stars being accreted into the supermassive black hole. And the way we can now directly observe these events is what we call tidal disruption events, which is this idea that as a star goes too close to a supermassive black hole, it gets disrupted. Roughly half of it is accreted and half of it gets thrown out. But the idea is that if you did this enough number of times over the age of a supermassive black hole, you could potentially grow it to scales that could at least explain the lowest mass supermassive black holes we see. It's an idea that's been around for many decades. The idea is that if you have roughly of the order of 1 solar mass of material that's being accreted per event, if you do this for a Hubble time, then depending on the rate, which is somewhat uncertain, you can actually explain the growth of at least the lightest supermassive black holes in the universe. But of course, the challenge here is finding these things and keeping in mind that these are some of the most obscured regions in the universe. This is, it's of course, an artist's depiction of what the center of a galaxy looks like. And we know that in our own galaxy, the Sagittarius A star is behind about 100 magnitudes of extinction. So the reason infrared, again, becomes a really powerful tool here is that it allows you to look at things that are very, very dust obscured. And the other critical part of this piece is that we want to measure how much mass is being accreted per event. The idea that if I can measure the energy output of that comes out of this event, you can relate that back to the mass accreted. But the problem, again, is that with supermassive black holes, most of the emission is in the far ultraviolet, which is almost unobservable directly because the universe is opaque in the far ultraviolet. But what the infrared helps you do is that if you have any tiny amounts of dust around the black hole, then you can have the dust that effectively acts as a bolometer for this radiation. This idea is that even if you don't see the central energy source directly, you can see the echo of the dust that's radiating some of this light. And if you could measure the energy output of the dust, you could relate it back to the energy output of the central energy source. So this is something that's been around. The idea to use dust echoes of TDEs to measure how much energy is being actually produced in these events. And the search for dust echoes of TDEs, of course, has a long history. And naturally, all of it started from ground-based efforts. So this is one of the earlier efforts where the idea was that you can take adaptive optics-based ground-based imaging to look for transients in the centers of galaxies. This is a tidal disruption event candidate that occurred in an ultra-luminous infrared galaxy. These are extremely dusty galaxies where you would expect to find events like obscure TDEs. And then this was naturally extended to looking at data from NEOWISE. The idea is that if you had multi-year cadence light curves of nearby galaxies, you could look for flares that would be produced by dust echoes of TDEs. It's an effective method, but one of the drawbacks at the time was that in order to effectively look for flares that are truly flares, you really have to get rid of the host galaxy light, which usually dominates the energy output of a galaxy. And so what we started doing a few years ago is this idea of using NEOWISE data directly as a time domain survey to do difference imaging directly in NEOWISE data and trying to look for transients. And here is a really nice example of that. So they have this science image from NEOWISE, something that was taken 10 years before. You subtract the two, is something that sticks out. And this is something you can easily do in archival data. And surprisingly, there was this huge mine of things that came out of that, and we won't have time to talk about all of that. But I was just talking to the Ofer yesterday about TNS. Should we post 5 million transients to TNS? Is that would that work? So there is a huge archive of transients in NeoWise data alone. Right. So this has led to some remarkable discoveries. As one, I think the most surprising of which has been that some of these events are really, really nearby. So this is a mid-infrared flare that occurred in a galaxy that's only 40 megaparsecs away. And based on purely energetic arguments, the amount of energy that's been radiated, you can show that the only way to explain why this flare occurred is that there was a tidal disruption event somewhere in 2014 at a distance of 40 megaparsecs that went overlooked for the 10 years. And just to show you how much discovery space there is in the infrared if you just apply the right techniques. And then Megan Masterson, who we'll hear from later today, went out and actually did this for the full sample and found that there was this population of tidal disruption events that only show up in the infrared bands, and these are quite common in the local universe. These are all TDs from NeoWise that have occurred within a volume of 200 megaparsecs, something that we think is the local universe, but apparently we've been missing all of these events. So I'll ask you to go to Megan's talk later in the afternoon, but you can actually use JWST to follow up these events and do this question of how much energy is being radiated in these events by measuring the dust output. And that's something we are actually able to do now, combining NeoWise and JWST follow-up. All right. So I want to go to the other end of this spectrum, which is the low mass stars. And I know many of you would be like, yeah, low mass stars, they're boring. They don't really do anything explosive. But I want to convince you otherwise, which is that there is good reason to believe that the end stages of the lives of low mass stars as well are quite explosive. And you don't need to look any further for evidence for this. If you just look at the remnants of low mass stars, these are what we call planetary nebulae. And what you can see immediately is that unlike sort of the spherical gravitational potential of a single star, the remnants of low mass stars don't actually look very spherical. They all have these weird shapes, dumbbells and cones and so on. And natural explanation that's been out there for many years is this idea that probably the reason why we get almost every planetary nebula looks like this is that architectures like these are very common in the universe, which is that it's not outrageous to say that probably every single star out there has a planet around it. And as this star evolves to become an AGB star and becomes huge in size, the presence of the planet sort of modifies the evolution of the star and produces potentially observable transients. So this is what we would call planetary engulfment. What you expect to see in these cases is this idea that as a planet enters the surface of a star, it sort of blows out the outer layers of the star and produces these shapes and also an observable transient. Now, in case you thought this was planetary engulfment, I fooled you, because this is actually two stars merging. But just to give you a sense, this is what a planetary engulfment looks like. So just to give you a sense that you can see that there's this uncanny resemblance between the two, which is that what you have is that because the planet is about 1,000 times less massive than a star, the effect it has on the star is much more subtle. Instead of this violent shakeup of the star that you see in a stellar merger, it's a much more subtle effect. So the historical expectation was that these look like stellar mergers, but sort of energies with energies of the order of 1,000 times lower. And this is great because we have some evidence of what stellar mergers look like. We call them luminous red novae. The idea that they have these short-lived optical outbursts that disappear in about a couple of months. The infrared emission can stay on for months and even years at a time, which means that they're, again, purely infrared transients that are most effectively found in the infrared. And we can now finally start combining the ground-based optical data with space-based infrared data to look for these events. And I want to show you one example where we think there is good evidence for that. This is a star that is in the galactic plane. You wouldn't quite pay attention to it unless it did something. Back in 2020, it did something spectacular. It had this huge outburst in Atlas and ZTF. And again, this is not something you would notice by itself. It's sort of a your run-of-the-mill galactic plane outburst until you fold in the infrared data. And you see that very much like a red nova, it has this ramp up in the infrared before the outburst and then has this long-lived infrared afterglow. It almost smells like a red nova, except the fact that this is a star in the galactic plane, and we can measure that the energy output is about a factor of 1,000 smaller than what we see in stellar mergers. And together with other pieces of evidence, what we think we see in these cases is that you have a planet that's starting to touch the surface of its host star as it's approaching the end of its life. this planet is losing orbital angular momentum. It's spiraling into the star in that process, throwing out this dust. And eventually, at the end stage of that, the frictional forces become so high that it crashes into the star and causes this brightening that we see in the optical bands. All right. So I won't get to talk about all the fun stuff that is there in this plot, but I encourage you to talk to the other folks who you've probably already heard talks from. So we heard yesterday from Danielle about young stars. Young stars go all kinds of outbursts in the infrared. We heard John talk about stellar mergers across the evolutionary life cycle. Go to Jeffrey Moore's poster if you want to hear about pre-supernova outbursts in supernovae. We heard Andrea about infrared outbursts from failed supernovae that form black holes. We'll hear today, Megan today, about these population of TDEs. And finally, Christos will also talk about these extreme nuclear accretion events. So this entire chain of things. So instead of just focusing on the supernovae, there's a lot more happening outside the supernovae. All right. So in the last couple of minutes, I do want to touch quickly on sort of what do we need to enable this landscape of discoveries in the next decade. And one of the things is that really starting to notice what are the science returns from being able to discover things in real time. So I'll go back to this example that we saw, the nearest TDE that went overlooked in surveys. At the time of peak, it would have been the brightest mid-infrared source in the extragalactic sky, but nobody was really looking for it. But it really goes to show that if you have real-time data delivery from missions, NEOWISE data was released only once a year, even though there was no reason for that, as far as I can tell. So if you were able to deliver data in real time and process this data for transients, this would be an incredible discovery machine from all space missions. And there are efforts from the Roman pits right now to enable this type of transient delivery in real time. I think another new frontier for space-based missions, especially combining this sort of 30-year legacy of Hubble data with these Roman surveys, is the idea of very long baselines, which is, we saw this example in the low energy transient session yesterday of this star that disappeared in M31. I think one of the key reasons we found it was because of the long baseline, because if you look at what PTF saw, PTF was just looking at this part of the light curve. PanSTARRS just looked at this part of the light curve, and ZTF only saw this part of the light curve. So individually, they don't seem very interesting because the star was either there or not there. But once you combine this entire baseline, you see that it actually did something spectacular. Just a luminous supergiant in M31 disappeared, and nobody noticed, because the baseline is what mattered in this case. So again, having archives of space-based, ground-based data where you can pull all of this together into a single portal. I think, again, one of the other things to keep in mind is that even if any mission that's looking at the sky again and again is a time domain machine. It doesn't have to be an astrophysics mission. And one thing I'm excited about is this idea of NeoSurveyor, which is the successor to NeoWise. It has this interesting scanning pattern that has cadences from hours to days. And it's about 10 times the volume of NeoWise in terms of data. And this will be, again, an incredible discovery machine for transients, only if we also think about transient discovery in non-astrophysics missions, because this is a planetary science mission as far as I can tell. So prioritizing follow-up in new regimes, one of the key unknowns, I think, in infrared transients is what happens in the far infrared band. So this is what the remnant of a stellar merger looks like a few years after the outburst. This is where we usually see and follow up these events. And you can see that by the time a few years after the outburst, these are gone. Even JWST can't follow up these things after a few years because they become so obscure. So the discovery space is really in the far infrared, and I'm really glad that one of the missions being considered right now is PRIMA, which is going to be completely pushing time domain into a new regime. And we're going to do far infrared for the first time after time domain became popular. The last time there was a far infrared mission was Herschel, which is quite a long time ago. And this is the same for if you think of TDEs. So this is some models that Megan created of what the dust echoes of TDEs look like a few years after the outburst. So yes, my final thing I'll say is that there's a lot of potential in joint processing from surveys. One of the key things that Roman is going to do is a galactic plane survey, where you can routinely identify progenitors of transients at a scale that's never been possible before, but by just combining, being able to process low-resolution ground-based data with high-resolution space-based data. And there's also synergies between looking at ultraviolet missions and infrared missions, because all of these CSM interaction signatures we see in the infrared are effectively powered by the same ultraviolet source that's inside. So this really helps break a lot of the JLCs, and it's really a discovery space for combining coordinated observations between different facilities. So with that, I will leave you and take any questions. These are some beautiful transients from NeoWise. Thank you.
Excellent talk. Thank you. Questions?
Shall I
Yes.
talk? Where did you get all your beautiful animations from?
Which one?
I've seen some of those.
Oh, I think the TDE ones have been around. Yeah, I think it was created by one of the neutrino campaigns.
All
Yes, yes.
all the dust echoes and all those.
Yeah, it was all the neutrino campaigns. Yes, from what I remember. And the planet engulfment was something we worked with folks at IPAC. Yes, that was an interesting project. Yes.
The TDE ones came out the same day the rover landed on Mars, so they were completely missed by everyone.
Good timing.
So I very much appreciate the point you made about using very old data. And I would like to make a comment to reinforce it. And it also is related to a question that was asked here about what can the community do to help. When we write proposals and ask the TAC to give us time for the next 20 years, or maybe not so extreme, next 5 years, for a long-term monitoring project, the results that we get back from the TAC are not encouraging. And even if we do get time, a year later, when we write a progress report, we're told, so where are your results? So my point here is we need a change of mindset, and we need to find a way to cultivate that change of mindset so that these very long projects that take patience and persistence can become more easy, more feasible.
Yep.
Very good point. Okay, let's thank you, Shlomo, one more time.
Sorry, you know that.
Okay,
So, Mike.
our next speaker is Federica Bianco, and she will talk about AI surveys.
Hello. My AI talk is sandwiched between two physics talks. So this is for something different. My name is Federica Bianco. My pronouns are she, her. I'm at the University of Delaware Department of Physics and Astronomy and Biden School of Public Policy and Administration and Data Science Institute. And I'm here to talk about, well, the talk title was Challenges and Opportunities in Machine Learning and AI for the Next Generation Astronomical Surveys. I've inverted the order of opportunities and challenges because I want to think positively about the opportunities. So the era of AI is, I'm going to argue, an opportunity for us in astrophysics and in transient astrophysics. What do I mean by the era of AI? So this actually is a description of the paradigms of science that came out in 2009 in a book that Jim Gray wrote. If you don't know who Jim Gray was, he was at Microsoft. He was really instrumental in building the infrastructure for STSS, which obviously chaperoned and ushered the era of big surveys in astronomy. And so he argued there have been shifts, paradigm shifts in scientific inference, and he could identify 4. Initially, and sort of from like minus infinity until the early 1900s, we were working in an experiment-driven framework. In the early 1900s, we shifted to a theory-driven framework with the principle of falsifiability. We started from a theory, and we were able to design better and better experiments, so we can design an experiment around the theory that we have, as opposed to derive the theory from the phenomenology that we observe. In the 1950s, we built computational resources that were incredible and allowed us to do like nuclear physics, the Manhattan Project, for better or worse. So that's a paradigm shift. We're into the era of computationally driven science. And then in the late 80s, early 90s, we entered the era of data-intensive science, sort of the era of big data, where sometimes we refer to big data as data that stresses the infrastructure that we have for extracting information from it. And so that's the era of the surveys like STSS, which again chaperone the large surveys that we think of today. But the point that Alex Salek, who's Bloomberg professor at JHU, who I had the honor to invite for a colloquium just last week at my university, he made the point we might be in a different shift right now. we might be in the paradigm of AI-driven science. So let me explore how that looks. And let me start by telling you what I mean in this talk, for the purpose of this talk, when I say machine learning and when I say AI. So machine learning, like the paradigm that, we're physicists, so we're interested in extracting physics, in understanding physics, understanding the physical world. We have data, those are our observations, and we used models, we use mathematics to approximate the processes that we think are happening in the physical world. And we do that by starting with the data, ending with a prediction that hopefully looks like the reality that we observe. And so what we have in between is a mathematical representation of the physics. So far, so good. So that's a function. And this function may be very simple. It may be a line, ax plus b. That function has two parameters. And when we say machine learning, really all that we mean is that we're using functions that have parameters which are being learned from the data. So there's a lot of mystification in AI and machine learning. So let me start demystifying this. When we do machine learning, we're just using parameter fitting, gradient descent. And so if your line looks like this, and your data is supernova, and you're looking at cosmology, you discover dark energy with a line fit, and you're an expert in machine learning. So most people in this room can call themselves experts in machine learning. Okay, let's look at a slightly more intimidating model for machine learning. This is a tree model. It's really nothing other than a flowchart, like a decision flowchart. Like, should I go to college? Do you like studying? Yes. No. This is what it is. What are we learning here? We're learning what are the pieces of decision. Where do we split the groups of data that we have? Maybe my input data is v minus I, color of an object. I will have a cutoff where I'm going to split my data into two groups. Split, 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 split. You end up at the end with a prediction. And this is this can become a fairly advanced method in machine learning. Maybe not just a single tree chart. Maybe you put it together into a bunch of tree charts, an ensemble model, like a random forest or a gradient boosted tree, fine. When I use a model like this, I'm going to have to extract information from the data to make that data ready for using my machine learning. So here, maybe I want to classify galaxies, and I'm going to do that by extracting some parametric shapes of the galaxy. So I'm going to have to do some modeling and some feature extraction from my data to be able to have it ready. I'm trying to get away from this light, which is super fun, to get it ready for my tree model. Then I feed my features to the tree model spits out a classification. So far, so good. So why is AI? Why am I arguing that we are now in the era of AI? We've been doing that for another 30 years, right? So for the purpose of this talk, and this is a very glib and inaccurate definition, and there's also like different definitions for different flavors and for different environments and different things you want to say. But let me just define AI as the framework in which we use neural networks. So now I've replaced my function with a neural network, which is just a network of simple functions. The functions can be as simple as just a slightly non-linear linear regression, a linear regression that is passed through a non-linear filter. I need that non-linearity for my model to be adaptable. Otherwise, I end up with the hardest to train linear regression, because mathematically that can be reduced to ax plus b. So each one of these neurons that we put in a neural network does some function. Maybe simple, maybe it's a little bit more complex. I put them together and have a really highly flexible model to approximate complex relationships between input and output that are typically highly nonlinear. The key point here is that I have not extracted the features. I did not decide what was important in my data to tell my model in order to understand how the physics work. I didn't tell it the color of the galaxy. I didn't tell it the parametric fit to the shape of the galaxy. I gave it an image of the galaxy, perhaps. This also has been around for a really long time. The first neural network concept appeared in 1943. In 1958, there was this article in the New York Times that I show in my classes all the time. At that point, all that model could do is distinguish left from right after hundreds of epochs of training. Binary classifier. And yet the insight at the time was the Navy revealed the embryo of an electronic computer today that is expected will be able to walk, talk, see, write, They can do all those things now, reproduce itself, thank God we're not there yet, and be conscious of its existence. And there is a true technical question about the consciousness of AI right now in both the technical community and the ethics of AI community. All right. In astronomy and astrophysics, neural networks have been around since the early 90s. In related disciplines like high energy physics, even in the 80s. What is so special about these models? Remember, they're super flexible, and so there is this kind of mystery about them, which really is something that we don't fully understand. We don't understand at all. That the amount of information that they're able to extract from a system, which I can measure as like how well they can do a prediction about that system. So here you have a loss curve, the inaccuracy of the prediction, versus the number of computations that you do, the number of epochs of training. Not exactly, but a proxy for that. That line just keeps going down. We have not found the point in which that line turns around. Furthermore, the more data I give you, that line also just goes down. This is a log, this is, oh no, sorry. This is a log natural scale. So it appears, for as far as we understand right now, that neural network have an infinite capacity of learning. I'm slightly cheating. We are now starting to see maybe a turnover in that line, maybe possibly, but it appears that they have an infinite capacity for learning, and they continue to scale their learning as they scale the computational resources and the amount of data. That's kind of a problem because we don't have infinite data, nor infinite resources, and resources aren't free, and I'll get back to that in a second. So now I have this proxy for my physics function, which we can argue might be hard to interpret. But even that, we have solutions for that. All these nodes are doing is creating an internal representation of the data, massaging the data until it looks right for my model to make the prediction, until it has extracted the right features from it. So if we can figure out a way to visualize, maybe more strictly, to interpret these series of neurons, maybe the ones that are closer to the prediction, the latent space of my neural network, then maybe I can even interpret it. Maybe I can even have my neural network teach me what is the physics that matters to make the prediction. This is a latent space of a model that one of my students wrote. I'll show you again in a minute to give you a sense of how this might work. That model does real bogus predictions, so differentiates between real and astrophysical and non-astrophysical transients in different images. And you see the locus of the red point is the bogus, the locus of the gray point is the real. It might be vice versa. It doesn't matter as an illustrative point. OK, so we are definitely in the era of big data and astronomy. And that is important because it's very hard to use neural networks with not enough data. Because remember, look at that. And we go 2 slides back. Look at the number of parameters that this model has, 175 billion. And you need a lot of data points to train a lot of parameters. Naively, you will think you need a lot more data points than the parameters. That actually is not true in neural network. That's another mystery. But you need a lot of data. OK, so we have a lot of data, so that's not a problem. I have some slides here that I'm going to skip through, but like LSST is coming up with 20 terabytes of data every night. If you know me, you know I've been working within LSST for a long time. We have other surveys in other domains like STScI that have been producing even more data. OK, lots of data, lots of transients, stars. Nobody cares about stars here. 17 billion stars, 10 million quasars. We now have 50,000 tidal disruption events. We now have 150, and so on and so forth. So we have a lot of data. And so hopefully we can use neural networks very effectively with this data. OK, let me show you just the discovery chain of astronomy. I'm going to go super quick through this and just give you a flavor of some of the opportunities for applications of AI. At every step of the time domain astronomy discovery chain, there is definitely opportunities for implementing AI solution. In discovery, which is a very fast-paced, rapid turnaround problem, as you know, traditionally we do this difference image, which involves solving a kernel locally. This is a very computationally intense process. We can now replace it with neural networks. For example, there's work by Sagam and Mahabal from 2017. We're given 2 pairs of images, template and science image. The neural network can predict what the difference image would look like. Let me skip over this just to show you my student, Tatiana Seroqueyer, worked on what can we do if we don't feed the difference image, but just the template and the source and the science image to a neural network and ask it, is it real or bogus? And we do find that we don't perform as well, so we still have a performance gap. But again, we can try and figure out how is the neural network learning. These are maps of features that the neural network is extracting from the images. They're saliency maps, so they tell you the importance of each pixel. And I particularly like this one, because when you do have a difference image, what the neural network does is primarily aperture photometry on the difference image. And look, it does it just like people do. It looks at the center of the PSF, and then it takes a little gap and doesn't care about that. That's no person zone that you don't look at it when you want to measure the background. Then you go a little bit further away and you measure the background, just like people do. Whereas when we don't have the difference image, we have to take a much more holistic view of the entire image set. And so you see that the pixels that are important become spread out everywhere. Again, we can look at the latent space to try and learn physics from these models. The distribution of alerts is entirely dominated by machine learning and AI. This is a snapshot from the ULTRASAT broker that distributes ZTF, LSST alerts to the community, also Antares and Think and many other brokers. They do filtering, outliers and anomaly detection, cross-matching, classification, feature extraction. All of those can be solved with machine learning and AI. And here's another challenge. Everything that we're going to do from now on is no longer image-based, at least not in the traditional analysis pipeline. So now I'm going to shift and work with light curves, maybe spectra. Light curves are actually very challenging for AI. And this is a problem of data encoding. If I had an image like the one before, I can just throw it into my neural network and it will work pixel by pixel, decide itself how to use the pixels. But really, feeding it a light curve is the equivalent of feeding it this image. I thank Alex Razin for this brilliant visualization. So this is what time domain astronomy work with. So we have it much harder than people that work on static science. If you're lucky, your light curve looks like this: tons of space data, infrared, ultraviolet, really long and extensive light curves from the ground. If you're a little bit less lucky, you might only have ground-based data, maybe only in 2-band. Maybe in a little bit fewer band, this is what LSST will look like. If you're in the deep drilling fields, this is what the majority of the LSST data will look like. So it's incredibly sparse. And if we want to fit a model, and then traditionally do a chi-square fitting of a model of a light curve to this data, we're going to have a large ambiguity because the data is gapping. Okay, so something that I'm just going to mention a couple of things from now on. Something that we obviously, one of the problems that we have will turn into a challenge, is that once we have the number of objects that I mentioned earlier, we just cannot rely on spectra for their classification. Alex Galliano put together this brilliant visualization of all the supernova that have been discovered over time, and on the histogram you see those that receive spectroscopic follow-up and those that don't receive spectroscopic follow-up, which trivially changes rapidly as we collect more data in photometry because spectroscopy is a lot more expensive. This challenge turned into a really brilliant opportunity for the astronomical community to develop light curve classifications with AI and machine learning. Gautam Narayam, who is here, was sort of the mastermind behind this. This is one of the masterminds anyways. This is a data challenge on Kaggle where we asked people, can you classify the light curves without the spectra and tell me what kind of transient it is? And you might think like, well, it's not that hard. If your light curve looks like this, it's a little bit harder if your light curve looks like this. And that's a simulation of an LSST light curve. And the problem is that when we do machine learning and AI, really all we're doing is matrix multiplications. We're really just doing linear algebra. And linear algebra doesn't like data that is gappy. It really likes squared box tensors that are the same shape for all the data points in all the dimensions. So light curves are variable in size and are variable size of data vectors. They're unevenly sampled. They have different sampling at different wavelengths, phase gaps, multiple relevant timescales. We have to be able to keep track of all the timescales at once. They have heteroscedastic error. Basically, they are a nightmare for machine learning and AI. Nonetheless, brilliant results from that challenge. This is the winner of that challenge, Kyle Boone avocado model. And here you have a confusion matrix of what the transients were and what they were predicted to be based on that photometry. And we even have made progress since then. But look at what you want to see is a confusion matrix that only has a diagonal line, because those are the right corrections in blue in this color scheme for your visual intuition. And this is actually really quite good. And it can be made better if you're interested, for example, in supernovae type 1a, because you're a cosmology fan. You can bias your model to be better at supernovae type 1a because you don't care about Myra or stripped envelope supernovae. Sorry, Miriam, I know you and I cared only about that. And if you think that the data that this model was based on looks like this, that should be pretty impressive, I think. Other models, Helen Kuh wrote a similar model that is also very popular now, that gets better accuracy. But let me just skip through the details just to mention there's a problem of encoding. To fix the problem with the gaps in the data, what Helen does, what many people do, is turn the data into a heat map by interpolating over the wavelength and over the time. There's also another trick that Helen did, which is she fit a similar map of the uncertainty in the data, because AI doesn't like uncertainties. They're not really designed to use aleatoric uncertainty, the uncertainty that you have from the observations. There's a solution to that. There's a couple of things that I want to say here. One is that there's solutions. Like I've showed you confusion matrices that demonstrate that we can do these things. But methodologically, in astrophysics, I think in the realm of AI, we actually do a lot of things that are a bit sketchy just because they work. That's okay, because we've seen that curve. Like they learn, they have infinite capacity for learning. So I'm just going to give it a little bit more data. Just going to give it a bit more computational resources. But we should identify these problems and try to solve them. For example, most recently, we have a lot of development in Bayesian neural networks that can understand the uncertainty on the data and make probabilistic predictions. Let me skip over this. Let me mention that in 2016 was a fairly disruptive year for AI and AI in astrophysics. In 2016, we had this paper called Attention is All We Need, Attention is All You Need, was one in 2017. And what they introduced is a method that uses the attention mechanism. In reality, the attention mechanism had already been introduced. What they actually introduced here is the multi-headed attention mechanism, but details. What is the attention mechanism? Well, if you have a series of data points, which in their conception was language, a series of words, in our conception, this is going to be time points in a time series. You can use that mechanism. Basically, you're asking a neural network to learn the covariance between the data. And the covariance is always what gets us, right? That's all that matters, really. That's what contains the physics of the processes that we're investigating. So this allows the model to independently learn the covariance if you want. The fact that it's a multi-headed attention means you can actually propose different ways in which you look at the covariance and put them together at the end. So now these are fairly applicable in astronomy. I see you, I'll take 2 minutes. And these are fairly applicable in astronomy. Again, details and development on technical details like the positional encoding. I'm going to skip over the rest because I want to talk about two things. Sorry, it's going to be a bit of skipping, but my slides are available. Survey optimization, that also can be enhanced with AI. Where is Adam? They just published, well, not even just anymore, but they recently published, ZTF recently published the first transient entirely discovered, observed, and follow-up spectroscopically while everybody was sleeping through AI. But I have two more things that I want to say. Oh, if you don't have a lot of data, like you high-Z people, physics-informed neural network combine physics constraints with neural network learning. But I want to ask you all a question. Do you like penguins? Who likes penguins? Please raise your hand. Okay, if you use AI, you are killing penguins. So AI is not like the resources that we need to train all those billions of parameters are not free. They have a carbon footprint. You can quantify the carbon footprint. Sorry about the placement of the flags in this slide. But this website allows you to do that. So let's just say, for the sake of argument, that I'm going to use a fairly standard GPU on the Google platform to train my neural network. And I'm going to run my neural network for 100 hours, which is a long time. But you're not running only one neural network, right? You're starting, it doesn't work, you change some things, it doesn't work, you change some things. 3 months later, I am sure you have exceeded these 100 hours. So let's see what your carbon footprint is. 14, oh, it grew. About half an hour earlier, it was 9.5 carbon kilograms of CO2 equivalent. Let me tell you what that is in a more tangible way. Pretend that it was 9.5 and not 14. You have spent the carbon. You have been responsible for the carbon footprint equivalent of 2.2 years of driving your car, 1,000 gallons of gasoline consumed, and you have heated your home with electricity for 2 years. And also a shout out to the EPA up there that provides this tool. There is a solution to this. Foundational models, which are the really big models like ChatGPT, 175 billion parameters. The models that are being built not by scientists, but by the industry, they can be fine-tuned, and that is not expensive. So you let them train for billions and billions of, you let Google train them for billions and billions of epochs, Google and Microsoft and all of those folks. And they learn to encode the data in their latent space. And the wisdom here is that in the earlier layers of a neural network, you encode general information. And then you really specialize for a task only in the last layers. So you don't train the whole thing. You chop off the head of the neural network, and you only train that. So now you're training a very small number of parameters. You don't need a lot of data. You don't need a lot of time. And this is happening in astrophysics. I didn't have the time to talk about multimodal model. That's another revolution in astrophysics. I'll take one more minute. For ethics of AI, you can't cut me off at ethics of AI. So obviously, I like AI. I really enjoy working at the frontier of AI and astrophysics, but AI is dangerous. I'm pitching here Joy Buolamwini, who is Dr. Joy Buolamwini from MIT, who did her PhD thesis on understanding racial bias in facial recognition software at MIT. And this is a brilliant book, Unmasking AI. And I'm going to make 3 points. Knowledge is power. Astrophysical data is a sandbox. It doesn't have a social value. It doesn't have a cost. We don't worry about the privacy of galaxies. We can learn AI on astrophysical data and learn really important things like how do we get rid of the bias? Where does the bias arise? With great powers comes great responsibility. So ethics of AI, and if you're a student here, learning about the ethics of AI is really imperative because you will have powerful tools at your hand. You might not end up in a faculty job where you apply them to Galaxy. You might end up working for, I don't know, an insurance company, applying them on predictions of whether people should be helped with their health or not. And then AI is a transferable skill, so you can choose to use it for good. One of my favorite examples of this is the same way in which we can recognize the position in the sky for an image by the patterns that the stars make. We can identify whale sharks, which are just about the most awesome animals in the world. And let me finish with Ruha Benjamin, also a professor at Princeton that works at the interface of race and technology. And let me give a shout out to the talk by Saurabh that we heard on the first day. So Ruha used this concept of astopia, a word that I'm borrowing from Margaret Atwood. It describes the fact that the future is us. However loathsome or loving we are, so we will be. Whereas utopias are the stuff of the dreams and dystopias are the stuff of the nightmares, astopias are what we create together when we're wide awake. I'm done. There's about twice as many slides in the slide.
It was an excellent talk, very controversial with some of the statements. So we have question maybe for 1 or 2 questions back here. Any questions?
Wolfgang, I had a slide about TARDIS. Sorry, I didn't get to it.
Very disappointed. That is a main comment.
Is that the question?
I had another question and maybe a thought-provoking question. I mean, for the longest time, and you showed like, we used the language of math, and then so we came up with ideas, and we realized now that like 3-body problem seems to be out of the grasp of this. So I had a very thought-provoking talk a couple of weeks ago where I learned about like what is physics. The question is posed here. What do we want in the end? Like, would we be happy if we present in a new base of functions that is maybe even more abstract than what we have now, a prediction machinery?
Right. And so if I understand the question, like the more, like the predictive power of models increases with the complexity of the model, but then the interpretability of the model decreases, right?
Whatever that means, interpretability.
Right. So our ability to understand what physical process the model is describing in terms of things that we understand in physics, in terms of forces, if you wish, is going down. And so I don't know what we need, but maybe it depends, right? Maybe in some cases it's fine to just be able to make a prediction because I'm automating a survey. I don't care about the interpretability. I care because I still need to have some layer of reliability, but I can get to reliability in other ways. But if I really want to learn physics, then I do need some way to get inside of the latent space and understand it. Whether that is an empirical study of the latent space, just see what's its structure. But there's also a lot of brilliant work by a number of people. I'm going to mention Max Tegmark here, right? That shows that these models that have sort of complex latent space representation, if you let them train for many more epochs, killing many more penguins, they actually represent themselves in an organized way, which is much more interpretable. So there are ways to extract physics. Maybe you don't want to do it all the time, though.
Let's thank Fred one more time. Our next talk will be about the host galaxy properties of.
Do I have a mic? Okay. Thank you. Sorry. Okay. Great. Hi, everybody. My name is Anya Nugent. I'm a postdoc at the CFA, and today I'll be telling you about how host galaxies are a very powerful tool in distinguishing transient types and understanding their progenitors, and how we can really take advantage of host studies to get the most exciting science results from Rubin and Roman. So I wanted to start off this talk by bringing up a question that the committee asked us to address in our slides, which is, what are some of the biggest opportunities and challenges that your field faces in the next 5 years, and what can we do now to prepare? So obviously, in transient astronomy, we are looking to some very exciting upcoming eras. We're going from detecting around 10,000 supernovae every single year to being able to discover millions of transients every year with Rubin. Now, moreover, in the next few years, we are also going to be rapidly expanding the redshift distributions for many of our supernova populations. So currently, with most of our transient surveys, we're detecting supernova out to about a redshift 0.5, 0.6, with very sparse detections of supernova beyond redshift 0.2. But with Roman, we are going to be detecting supernova up to very far cosmological distances. Now, obviously, this is really exciting as we're going to have this large type 1a supernova population, which we can use for cosmology studies, which was discussed earlier today. But also, we're going to really be able to understand how many of our supernova have evolved with cosmic time. But obviously, we face the same problem with both Rubin and Roman, in that we are going to be detecting many more transients than we can feasibly follow up or even get spectroscopic classifications for. So many of us right now are asking, how do we actually go about identifying the transients that we want to be studying and building sufficient and robust samples so that we can do all of this exciting science and take advantage of all these cool events that we're going to be discovering in the next few years? So there are many ways that people are going about addressing this problem, but today I hope to convince you that host galaxies are really cool and we should really be using them to do this. And this is because while many of the transients will fade away long before we've had the chance to decide whether or not they were cool enough to follow up with our own observing programs, the host galaxies are always going to be there for us to study. And host galaxies have already been very pivotal in distinguishing transient types and helping us better understand their progenitors. So with host galaxies, we can understand how transients trace different properties like stellar mass and star formation, which we see in this plot over here, a bunch of different transient host populations, and we can see that our older stellar progenitors, like short GRBs and type 1a supernova, are tracing galaxies with higher stellar mass and lower star formation than our core collapse populations. I think that this is also highlighted very well in this plot from Steve Schultz's core collapse supernova host galaxy paper, where he's looking at a bunch of core collapse populations along the star forming main sequence, so star formation rate versus stellar mass. And we can see that they're all occupying a very different space within this regime. Now, another thing that we can get from host galaxies is metallicity. And now we know many of the progenitors of our supernova are going to be very metallicity dependent. And most of the time, we can only be getting metallicities by looking at the host galaxies. So I think that this paper does a really good job of highlighting that different supernova populations are occupying distinct regions of metallicity. So not only can metallicity be a distinguishing factor in helping us identify the transient, but also this can be really useful in better understanding the progenitor and its formation channels. So host galaxy studies have been great, but the way that we are currently studying hosts is not quite going to cut it for Rubin and Roman. And this is because the SED fitting techniques that we're currently using are just way too slow and computationally expensive. So I would say the most popular method for getting stellar population properties is really state-of-the-art stellar population modeling inference code called Prospector. Basically, you hand Prospector your host galaxy photometry. It runs a nested sampling fitting routine over the prior space of all the stellar population properties you're interested in, making many model calls and likelihood calls to get you a best fit model spectral energy distribution and posterior distributions on the stellar population properties of interest. Now, all of those model and likelihood calls are extremely expensive. And in my experience, Prospector fits can take anywhere between 30 minutes to 2 hours, 2 days, depending on the breadth of your observational data set, how noisy your data is, and the complexity of the model that you're using. So if we're thinking about all of the transients that we're going to be detecting with Rubin and Roman and all of the host galaxies that we want to fit, that's probably going to take like several billion years on a supercomputer to do all of that, which I don't know that any of us have that much time or want to be using all of our supercomputer resources on that. But luckily, there has been a recent solution to this computational complexity, and this is by using something called simulation-based inference. So basically, SBI uses normalizing flows to learn posterior density distributions. So essentially, we can give SBI mock photometry from the surveys that we're interested in using for our host galaxy studies, and it can learn Prospector simulated stellar population property posterior distributions from that mock photometry, and then we can use that on all of our observed host galaxies without making these very expensive model calls. Now, this has actually already been tested very successfully in this paper led by Bingji Wang, and they call their model SBI++, and it has the added benefit of including cases where we might have a missing photometric band or very noisy photometry within our galaxy SED datasets. Now, what they saw here is that SBI++ was able to reproduce similar posterior distributions as traditional Prospector nested sampling methods, but in a fraction of the time. Typical SBI++ fits take around 5 to 10 minutes on your laptop, which is great. Now, another thing that they noticed was that SBI++ produce more realistic and accurate uncertainties than traditional nested sampling methods. And I think this is highlighted very well in the middle panel over here, where we're looking at photometric redshifts produced from SBI++ in the red compared to our traditional nested sampling methods in the black versus the true galaxy spectroscopic redshift. And what you'll see here is that there's a handful of cases where traditional nested sampling methods are grossly under or overestimating the true redshift of the host galaxy, whereas SBI++ is able to have larger uncertainties that typically encapsulate what the true redshift of the host actually is. And the great thing is that SBI++ is actually already in use with the BLAST web app to determine host galaxy stellar population properties. So I have the URL down below if you can see this, but BLAST is great. Essentially, you just hand it an RA index of your transient and a spectroscopic redshift if you have one, and it goes ahead and makes a host association for you. It does aperture photometry using a variety of galaxy surveys, and then puts that photometry through its SBI++ model to get you your stellar population properties. So the current BLAST SBI++ model does have a few limitations. It only works for galaxies out to redshift 0.2. And as I mentioned before, we're detecting transients out to about a redshift 0.5, 0.6 right now. So this does not help for all of the different transients that we might want to study. And moreover, it does not have a way to sample redshift or have redshift as a free parameter within its fits. So it's pulling a spectroscopic redshift if one is available for the host galaxy, or a photometric redshift available from surveys like TESS if it does not have one, and using that instead of sampling itself. So we wanted to have a case where we could have redshift free fits, as I just showed you. SBI++ seems to be doing a better job at determining redshift than these other methods. And then we wanted to test these new methods out on a large supernova sample to determine if spectroscopically versus photometrically classified transients trace different host properties, potentially leading us to conclude whether or not transients are being misclassified, or how helpful host galaxies will be in distinguishing these transient types, and then also use this information to infer progenitor channels and environmental properties from a variety of supernova. So our test sample is the YZ-DR1 supernova sample. This comprises about 500 spectroscopically classified supernova and 1,500 photometrically classified supernova, out to about a redshift of 0.6. I don't have time to go over host associations today, but we're having a lot of success with the method that we're using. So if you're curious, please come find me and I'll talk to you about it. And then, as I mentioned, we wanted to update our SBI++ model. So we basically built a model from simulated noise depth photometry from a variety of public surveys and prospector non-parametric star formation history stellar population models. And so I'm just going to show you a few examples of what our SED fits look like. So this is an example of a host galaxy where we didn't have a spectroscopic redshift. So we had SBI++ give us a photometric redshift, and it did a very good job at producing a model spectral energy distribution, and then also giving us a very constrained star formation history. This is another case where we didn't have a spectroscopic redshift and we only had 5 bands of optical photometry, but even with that limited data, SBI++ was able to show us that this galaxy has a very clear rising star formation history, and that's going to be really useful information for when we're doing delay time inference for these different populations. And then finally, I thought this was a good example of what a noisy photometric data set might look like. And you can see that even with all of this noise, SBI++ was able to find a pretty good model SED that fits the data. And now that does lead to some compromise on the certainty on stellar population properties in the star formation history, but this is still usable within our analysis. Okay, and then I'm just going to go through some preliminary results that we have with the YZ-DR1 dataset. We are planning on expanding this sample, so this is very preliminary plots. So here I have 3 different classes of supernova host galaxies plotted along the specific star formation rate versus stellar mass plane. This black dashed line over here represents the star forming main sequence, which is where star forming galaxies move along as they gain in stellar mass until eventually they're no longer star forming. And we can see in all 3 of these cases, the supernova trace very different parts of the star forming main sequence. And this is going to be really important information in helping us distinguish these transients, but also get the most information about their progenitors and how they might be dependent on things like stellar mass and star formation for their progenitor formation. And then finally, I also mentioned that we want to be comparing our photometrically classified supernova to our spectroscopically classified supernova to see if there are any differences, understand when transients might be misclassified. But we do have this big issue in that our photometrically classified transients tend to be occurring at higher redshifts than our spectroscopically classified one. And that is just automatically going to lead to a difference in host stellar population properties, as many properties like stellar mass, star formation, and metallicity are highly redshift dependent. So what do we do about that? This is certainly something that we need to be thinking about, especially for transients we'll be detecting with Roman, as I expect that many of the galaxies we'll be detecting at high redshift hosting these events are going to look very different than our current host galaxy samples. Okay, I'm almost done. So bringing it back to this first slide, the time is now to really understand how host galaxies will play an important role in identifying transients and distinguishing transient types in the Rubin and Roman era. So what do we need to do? We need to develop fast, reliable methods for determining host galaxy properties. I hope that I've convinced you that we have that and we've done that successfully, and then use those host properties to determine when they are useful in identifying misclassified transients and distinguishing transient types, and then eventually use all of this huge host population for progenitor studies, delay time inference on a variety of transients. So in conclusion, so we have built a fast and reliable method that can give us our stellar population properties for a bunch of host galaxies in a very fast amount of time. It takes like, I think, 15 minutes tops to make a host association to get you till you can get your stellar population properties. And we plan to put all of our methods on blast, so those will be publicly available hopefully soon for all of you guys to use. And I'll just finish off with, I hope that I've convinced you that host galaxies are important and that we should really be taking advantage of host studies in these next few years. So thank you very much.
Thank you.
Does your SPI++ still have this redshift upper limit right now?
Yes, so we've capped it at about redshift 0.6.
Yeah. What's the reason for this cap? Is it because of thinking of training set?
Yeah, so it's basically because we're not detecting any transients beyond redshift 0.6. There's very few transients even detected beyond redshift 0.2. And I don't think we've seen many cases where we need to, or it looks like it's hitting that upper limit and we need to increase that. But that's certainly something we should think about for the future, especially when we're detecting higher redshift transients. It's easy enough to just build a new training set with higher redshifts and see what it does.
Question.
Thank you so much for this wonderful talk. So one thing I was wondering, I mean, galaxies and very photometric redshifts for galaxies,
yeah,
is a huge field, right?
Yeah.
Transients. So I was wondering what's kind of so special about your algorithm, if you can explain it, because I mean, since you mentioned it's so quick and so reliable, and you have huge implications for lots of fields that work on galaxies.
For sure. And the original paper that I showed that introduced this method was a galaxy paper. And so I think that they'll definitely be planning on using that for galaxy studies as a whole, especially like JWST targets. The original one, the paper that I was showing, was actually built to determine redshifts for JWST targets.
Let's thank Anya one more time. Okay, our last speaker of this session is by Netzka, and he will talk about the landscape of extreme and exotic transients.
Okay, it's a pleasure to be here. I did not give myself this title. This was the title given to me by the organizers, so I had to decide what is extreme and what is exotic, and I came up with some things to talk about. I don't really have a plan other than to go through some of these things that you may not think about every single day. Okay. So I think one thing I want to emphasize is that no matter how energetic an explosion is, it won't be luminous unless something keeps the debris hot until the photons can get out. And this thing that's keeping the ejecta hot is one way to classify different types of transients. So you have radioactivity, of course, the decay of nickel to cobalt to iron, or our process. Some transients are powered like stellar merger transients from recombination of hydrogen potentially. Another thing is you can have an explosion that runs into some pre-existing circumstellar medium and there's a shock wave, or maybe it runs into some earlier material ejected from the same explosion. And then a final possibility is you have some type of central compact object, an accreting black hole or magnetar in the center that's sort of powering from the center. And so this is one way to sort of classify different types of transients. So you have things like supernova 1A that are mostly powered by radioactivity. You have things like GRB afterglows that are mostly powered by a shock. You have things like prompt emission from GRBs are mostly powered by a central engine. But then you have things that, we're still debating what's powering them, or they could have multiple power sources. And sort of disentangling this is one of the goals that we have with transients, is then to turn these around into probes of the medium or the nucleosynthesis or the central engines. So over my career, I've worked on a number of these things, and I have strong opinions on the things that are bolded. So if you'd be interested to talk about any of these, I'd be happy to. I obviously don't have time to talk about all of them in this conference. I'm going to sort of jump through a few examples today. So one of them I'll start with are radioactive powered transients. So we're all aware, 8 years ago, we saw this beautiful neutron star merger from LIGO. When the two stars collide, they eject this very dense neutron-rich material into space. As it expands, it creates these heavy elements, which are radioactive, and that's what keeps the ejecta hot and causes the kilonova emission that we saw. And of course, we have this beautiful light curve for this particular event. And so by measuring the luminosity of these events, we learned something about the total radioactive power, which tells us about how much mass was ejected. By measuring the time scales and colors, we learned something about how the ejecta is trapping photons, which tells us something about the opacity. And that in turn tells us something about the composition. So if you have heavier R process elements, they trap the optical UV radiation longer, so you get something in the infrared. If you have just the lighter ones, it gets out faster. You might have both. And by sort of modeling this, we can roughly infer how much mass is ejected and with what speeds, et cetera. But underlying this is some overall radioactive power decay, which we think for our process is going like T to the minus 1.2 or something. It's a statistical ensemble of decaying nuclei. But I think we're still debating, are the mergers the only R process source? So I think one thing that gives us hesitation is that we see a lot of R process happening very early in the history of our galaxy, even before it's possible that we have that many mergers going on in ultra faint dwarf galaxies like Reticulum 2. Is it possible to keep a binary neutron star in a galaxy with an escape speed of 10 kilometers per second, long enough to enrich these heavy elements? When you look at the ratio of europium to iron over as a function of metallicity, you see it's higher in the past, which tells us that much of the europium was produced before the iron, and the iron comes from 1A supernova. So this tells us a lot of our process was happening early on. Maybe mergers can do this, but maybe we need sources that more directly trace star formation. And one such source, I thought about several that I think is becoming increasingly relevant, are magnetar giant flares. So magnetars are these highly magnetized neutron stars in our galaxy whose missions is powered by the decay of their magnetic fields. They emit a range of flares on a range of time scales, but the most energetic ones are the giant flares, which release 10 to the 45, 46 ergs. There have been 3 of these in our galaxy and the LNC over the last several decades. And sometimes we can even see these outside of our galaxy where they appear as short gamma ray bursts. So there's 2 phases to the gamma ray emission from these giant flares. This initial prompt spike, which is some kind of recombination event creating a pair of fireball above the surface, which radiates gamma rays. And then as that fireball leaves, a portion of it's trapped in the magnetosphere, and as the star rotates, you get this rotationally modulated X-ray tail as that fireball evaporates. For the 98 flare and the 2004 flare, the most famous one 20 years ago, there was a radio afterglow, which tells us already that there was mass ejection from this event. And by modeling this radio afterglow, you can infer up to a millionth of a solar mass was ejected at a few tenths the speed of light. So with student Jakob Sahula at Charles University, we attempted to understand one way that this mass could physically be ejected. And the physical model, which is extremely simple, is we imagine the reconnection event creates a high pressure region above the surface of the neutron star. That drives a shock wave into the crust, and then as that high pressure region, the pair fireball, goes away, the crust finds itself overpressurized and re-expands kind of like a spring uncoiling. And this can eject mass into space with a range of speeds. And we showed that for reasonable energetics, it was possible to reproduce the mass ejection inferred for the 2004 flare. So with my student, Ani Patel at Columbia, he explored what types of nucleosynthesis happens in this decompressing neutron star crust material. So this is a model for a millionth of a solar mass. If you go that depth below a neutron star, the electron fraction is about 0.4, so it's quite neutron rich. And indeed, as this hot expanding material decompresses, you can form heavy elements, mainly first and second R process peak elements. But these are radioactive, just like in a kilonova. These elements you create are radioactive, so you have this radioactive decay of the expanding material after the giant flare. And this, in principle, could power an analog to a kilonova, but because the ejecta mass, so the radioactive decay is releasing beta decay electrons and gamma rays, they're heating the ejecta. But because the mass is 10,000 times smaller than a typical cubic kilonova, rather than peaking on several day time scale, it peaks on about 10 or 15 minute time scale. Luminosities 10 to the 39 to 10 to the 40 ergs per second. But nevertheless, if you had a magnetar that wasn't behind huge amounts of dust in the galaxy or an extragalactic magnetar, we estimate that this could be detected out to a few megaparsecs. And I think an exciting possibility is you trigger on the gamma rays and then rapidly slew a space-based telescope like UVEX or ULTRASAT, probably ULTRASAT's better, to try to detect this decaying signal. But I want to talk a little bit about how we may have confirmation that this already happened in the 2004 flare. So I already mentioned that you have these two phases to the gamma ray emission. But you have these expanding radioactive material you've ejected. As I said, it releases gamma rays. And you can ask, OK, when do I get to see those gamma rays escaping, as opposed to thermalizing their energy? Well, you can just take the ejecta mass, estimate how long it takes the expanding material to become optically thin to gamma rays, and it takes about 10 minutes. So you would expect, if there was R process production in a giant flare, you'd expect to start seeing gamma rays from those decaying nuclei. And indeed, as we look back in the observations in the 2004 flare, after the X-ray tail had faded, there was an additional quote-unquote MEV afterglow that was detected by Integral, as well as CONUS Wind and RESI. And as far as we could tell, nobody ever explained this event, but we found that it matched very nicely what we expect from R process decay, peaking on a time scale of about 10 minutes and then decaying roughly as a power law. So this could have been, in principle, the first kilonova 20 years ago. So my student calculated Ani calculated more detail, the gamma ray line emission. I'm not going to go into the details. Each of these isotopes emits a forest of gamma ray lines, and you can calculate the total energy released. You can account for its absorption and then escape. And anyways, you can fit a gamma ray light curve model pretty well to this observed MEV afterglow if you assume that a millionth of a solar mass was ejected. And I should emphasize that you can reproduce the time scale, the decay rate, and the fluence, all for a consistent ejecta mass, which is consistent with what was inferred earlier from the radio data. So to us, this is pretty compelling evidence. There's also the spectrum. So the gamma ray emission is a forest of gamma ray emission lines, which have been Doppler broadened by the expansion into a quasi-continuum. And so you predict roughly a flat continuum up to a few MeV and a cutoff, and that was consistent with what RESI claimed the spectrum was. So this is quite exciting. Maybe magnetar flares are contributing to the galactic R process. How much? Well, these giant flares like the 2004 are probably kind of once per century events. This one ejected 10 to the minus 6 solar masses. So if you multiply the rate and the yield from this event, and you can kind of put it on this diagram, which tells you that these giant flares could maybe contribute a few to maybe 10% of the galactic R process. But unlike mergers, they should very promptly trace star formation. And so this is a good potentiality to explain R process production in very old stars. I'm not going to talk. I've sort of put together for each of these. I was one of the few speakers who follow the orders and put together some questions about each of these. I just say that there's a lot we're still trying to learn about kilonova. We get better samples of kilonova, but there are other sources. And it would be really great if we had another giant flare where COSY is flying so that we could actually test whether these bumps are in the spectrum. RESI didn't have enough sensitivity to do that. I want to move on and talk about a shock-powered source, or what I think is a shock-powered source, which are QPEs. So these are, DJ already talked about these events. I should have cited his work. There's been a huge amount of work on these, but So there's 10 systems known. They have these periods from hours to a few days, these duty cycles of tens of percent. They reach peak luminosities of order 10 to the 42 in these eruptions. And they're seen in fairly low mass galaxies. 1 in every 10 to the 5 low mass galaxies has one of these QPEs popping off in it. And so the eruption properties are quite interesting. The light curves peak, they're narrower and peak earlier at higher X-ray energies, and then more. They're pretty soft transients overall, but then they peak more, the wider light curves at lower energies. Underlying many of these sources, we think, is the accreting central supermassive black hole. But then the eruption, these QPEs are basically where the spectrum suddenly gets harder above that sort of quiescent accretion disk emission, which is very soft. It's not also seen in all of the events. So there have been a number of theoretical models for what these QPE sources are. Julian's here, he's worked on one of these. You have instabilities in the accretion disk, maybe lensing. A lot of models have honed in on some kind of orbiting compact object, which is either feeding mass under the black hole or hitting an accretion disk or something. And I worked on one of the early models here I'm not going to talk about today. But I think our hint is kind of that these orbital periods out, these periods that are seen are kind of order hours, which is roughly the orbital period of an object very close to the tidal radius of the supermassive black hole. But I think one important clue that is difficult for many of these models is that these are not strictly periodic, these QPEs. Some of them exhibit this interesting variation in the timing where consecutive QPEs are sort of, there's a short interval and then a long interval and a short interval, and they kind of vary back and forth by order 10%. And I think there's sort of one model that we focused on and other people have thought about as well that I think can explain this type of behavior. So the idea is that you have a star which comes into the galactic nucleus probably through gravitational waves, so it's on a nearly circular orbit around the supermassive black hole. And then something creates an accretion disk now in a different plane. And so that star, which is orbiting at a few tenths the speed of light, is periodically every orbit, twice per orbit, colliding with the accretion disk. And the idea is every time it hits the disk, you get a flare of emission. And I'll talk about in a second how that is. But if the orbit is mildly eccentric, then of course you'll spend a little bit more time on the apocenter side than the pericenter side. And so you'll naturally get this kind of long, short timing if you can see these flares from either side of the accretion disk. So with Indra Groom and Itai, we explored whether this is quantitatively possible. We did some radiation hydrodynamical simulations of a star passing through a disk. So the star is going through the disk, it shocks the disk material. If the disk is not too thick, that little cap of shock material stays ahead of the star, can't flow around it. And when the star comes out, that overpressurized material expands, and you get kind of like a little miniature X-ray supernova of this hot expanding debris. In detail, you have to follow the photon production, the Comptonization, et cetera, but we found that you could reproduce this effect that at higher X-ray energies, the light curves are narrower, and then at lower energies, they're wider for the same reason that supernova are narrower at bluer bands than redder bands. And that you could get hard enough emission that you would get this QPE flare sticking out above the quiescent emission of the disk. One of the interesting associations that has been identified is that QPEs seem to have some association with TDEs. So if the first QPE source, GSN 069, if you went back a decade, it was the quiescent emission from the black hole was brighter, and this was interpreted as a TDE that had been fading for a decade before the QPEs appeared. And then most recently, we have this amazing example from Matt Nickel et al., 19QIZ, where there was a bona fide nearby TDE, and then the QPE started popping out several years later. They think roughly when the accretion disk from the TDE expanded sufficiently to intercept the orbit of the body that has that period. So there is naturally an expectation in this model, you could call it a prediction, although, as we said, there was some evidence for this before, that you should have a connection between TDs and QPs. And the idea is that this star is coming in through gravitational waves very slowly. So in going from like 6 to 3 tidal radii, it spends 1 million years, whereas TDs happen in a nucleus every 10,000 years. So it's inevitable that every emery that comes in has to interact with a TDE. And you can inverse that, and you find that a sizable fraction of TDEs should find themselves happening where there's these emeries. And so it's natural to expect this kind of connection. In terms of future space-based implications, I think one thing to think about is whether QPEs are exclusively an X-ray phenomenon. As I mentioned, we think the way you see them is basically that you have the quiescent disk, and then the QPE is becoming harder than the quiescent emission. But it's also possible in lower mass black holes that the disk emission could be harder, and then the QPE could pop out could be softer and pop out above the Raleigh gene's tail of the disk. So you could imagine there being some ultraviolet analog to QPEs, and that would be very exciting to see with these future missions. Number of burning questions and goals. I'm not going to go through these. There's a lot of open questions in how TDEs and QPEs connect, whether these stars will eventually get destroyed, lots of other things. All right, I'm going to spend a little time. Let's see, where am I at on time? Anyways, talk about superluminous supernova now. Okay. So we've heard, we all know superluminous supernova are the ones that are too bright, most of them to be powered by radioactive decay. And if I'm going to focus in on the type 1s, where I think the type 2s we're pretty sure are mostly circumstellar interaction, but we still have this debate whether the type 1s are some kind of central engine or circumstellar interaction. I'm going to talk about magnetar models. So the idea, one of the ideas for powering these is that you have a central engine, a rapidly spinning neutron star, which is pumping energy into the ejecta, making these things brighter. If you have a millisecond neutron star, it has quite an enormous rotational energy. If it has a strong magnetic field, moderately strong, it will spin down in a few days and deposit that rotational energy, which the idea is that then that heats the ejecta, and then the ejecta radiates as optical radiation. And the reason that these are so bright in this scenario is that the spin down time is sort of comparable to the optical diffusion time. So the energy you release through spin down can be efficiently radiated. So you can tap into this 10 to the 52 ergs of rotational energy and make your supernova much brighter. But there's kind of this, this is hard to test because in the end, we're just saying the pulsar is like a source of energy, and through some magic, its energy is thermalized by the ejecta, and it could be another source. It could be shocks that are providing the heating. But of course, if you assume this, so you assume 100% thermalization, then you can model the light curves and extract the magnetar properties, and everyone does this. It's great. It teaches us about the birth properties of magnetars, that this is right. But this is a pretty strong assumption that you get this 100% thermalization. We actually know in the center, if there's really a pulsar, it's very non-thermal thing. So when do we get to see the pulsar appear? Well, we already have some evidence that if there is a neutron star in some of these systems, that the light curves are certainly dropping below what you'd expect for the decaying magnetar luminosity. So there's this question, okay, where is the energy leaking out? That if really optically these are fake, there's really this energy being dumped in. We don't think the energy from a central engine is escaping at X-rays. The ejecta's X-ray opacity is way too high, and we don't see X-rays from most of these. We can rule out that the magnetar's luminosity is coming out in X-rays, but it could be coming out at higher energies. And so with Indra Groom, again, we did some Monte Carlo radiation transfer simulation several years ago, where we follow the injection of electron-positron pairs from the pulsar into the nebula. We follow the cooling of the nebula, the inverse Compton, the synchrotron radiation, which makes gamma rays, and then we followed how many of these gamma rays actually escape and how many of them are thermalized in the ejecta, which can then produce the optical radiation. If you look at the ejecta optical depth as a function of time, so there's sort of high opacity at X-ray energies and high opacity at TeV energies. But in the MEV to GeV range, there's this kind of window of low opacity. So that's the first place that the radiation will get out. And so what you can show is that it's indeed true near the optical peak that most of the magnetar's luminosity will thermalize. So that part of the modeling is on safe ground. But then a few months after the event, you should start to see GeV emission coming out. And then eventually, in a few years, you should start to see even higher energy gamma rays coming out as the ejecta becomes transparent to gamma-gamma. And in fact, with David Ribeiro at Columbia, we tried to constrain this. We didn't see, we're sort of on the borderline of constraining this. There was a very radical claim last year that Fermilab had actually made a GeV detection of one of these nearby superluminous supernova, which fit very nicely with our theoretical models. But I think there needs to be more effort in this direction, because this is how you confirm there's really a magnetar. Okay, nothing else is going to make GeV emission than a central compact doctrine. Probably. You could do it with shocks, but you're not going to get this bright of GeV emission. Okay, but I want to tell you another way to test for whether there's a central engine. So you might ask, okay, if there's a pulsar in the middle, it's putting a lot of its energy into this pulsar wind. Some fraction of it could well go into a jet. And it's theoretically possible for this central engine to launch a jet. Of course, the star is already exploding in this scenario, so it's a little different than a GRB. But it's actually easier, even though the engines in superluminous supernova are weaker than in GRBs, it's actually easier for a jet to go through a star that's already exploding. So theoretically, we expect if there is a central engine, it could launch a successful jet, but we don't see any evidence in terms of off-axis radio emission. But one thing we do see in a lot of superluminous supernova, these early sort of bumps, pre-maximum bumps. And it's possible that's CSM interaction, but it's also possible that that could be cocoon emission from a jet that is broken out. and the expanding interface between the jet and the ejecta powers thermal radiation. And so with Orr Gottlieb, we looked at we did a hydrodynamic simulation of an exploding star where we then launched a jet which had a duration and luminosity commensurate with the time of magnetars we need to power the later superluminous supernova emission. And indeed, get a very bright cocoon that would produce something peaking on a few days in the UV and optical. So at least it's possible. What we really need to get is early spectra to look for very high velocity features that would be indicative of a jet, and it would be great if we could detect something from the orphan afterglow if these are really around. More burning questions. All right, where am I at?
Like 1 minute.
1 minute. Okay, I'm going to finish F-bots. Don't know what they are. I like models that involve tidal disruptions of stars and binaries, because I think you can naturally get a lot of CSM and you get the huge accretion disk from binaries. All right. And I think, and so I think there actually is a whole range. If you have, common envelopes and binaries as a function of, the time you get a merger between a black hole and a compact object after a common envelope event, I think there's a possibility for getting a whole range of transients from luminous type 2s, to just completely stripped interacting things. But all right, I'm going to finish. I'm going to just finish. Going to talk about white dwarf neutron star mergers. Don't have time. They're also interesting. So I think, anyways, my not so extreme exotic conclusions are: I think one thing is that you discover a phenomenon one band, and then I think a lot of it is then coming back at a different band and recognize and being able to test some of these ideas at different bands, and I think there are a lot of connections between these things and understanding some. I mean, I'll give you an example. I study classical nova very closely, shocks in classical nova, and as a result of that, I think I understand better how shocks might work in two ends, and their nova are much closer. We can learn much more about them. So, anyways, I'll finish there. Thanks.
Thank you. Fine. Any questions?
So for the case of superluminous supernova, if we assume that the energy is leaking through gamma rays or X-rays, can we also have the possibility of maybe neutrinos that be detected from them?
Yeah, there should definitely be some neutrinos associated. I haven't given much thought. It's probably not particularly luminous, so I don't know whether it would be good for like individual point, like individual neutrinos. Sort of background from that. There definitely, these interactions, there definitely are neutrinos. It's just not going to be as bright as a relativistic jet pointed at you or something.
About the superluminous supernovae, about the radio emission, you mentioned very quickly that there was a lack of radio detection. Yeah. I was wondering, like, what timescale, what frequency, because he says it might not emerge until... Probably not the best answer to this. Is from Jean Comminjan's paper. I guess it looks like most of the upper limits are kind of on timescales of sort of months. And that would be sort of the, I guess, the timescale months to sort of years that you'd expect this off-axis after emission to appear. It's just I don't think we have much knowledge of what the ISM, this ISM densities are around these, and so really turning a radio non-detection into like some robust constraint is challenging.
It's actually related to this question. I mean, there was this ultra long GRB that was connected with the superluminous superhost with the 2011 KE.
Right.
Is that something you thought including here, or because I think it was very
Yeah, I think that's an example of that would be something where the engine is between those of most GRBs have engines that last minutes. Most superluminous supernova require engines lasting days. And that was like a 10 to the 4 second engine that's the supernova that's between these two extremes. So I think that's an transition case. Yeah.
Okay, let's sync all those speakers one more time.
Okay. Great morning. I know everybody's probably very hungry, as am I. But while we have your attention, we're going to do the group photo right now. Okay. right outside, so everyone needs to be as efficient as possible. For my wedding, I hired the one photographer that had an infrared camera. But the only difference in that photo was that I had white hair, and I was going to make this great joke about today, but it turns out there's very little white hair in here. Everyone looks very young. I'm very impressed. So anyway, we don't have an infrared camera outside. You can go out the side door or right out the front. If you need a bathroom break, please take it, but make it fast. And also, if you have dietary restrictions, please make sure to see the caterer. We have your meals. I know there was some confusion. We have your meals. All right.